What does Mars's reddish hue have to do with its watery history? We'll talk about it this week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. Mars has been red for billions of years, but scientists may have finally cracked the case on what iron compound actually gives it that color. This week I speak with planetary scientist Adomas, or Adam Valantinas, from Brown University. He's the lead author on a new study that suggests that Mars's surface dust is dominated not by hematite, as we long believed, but by a different water-rich mineral, ferrihydrite. What does that mean for Mars's watery past? We'll get into the science, the implications for future human explorers on Mars, and what it tells us about the red planet's timeline for habitability. Then we'll revisit one of the most iconic discoveries in Martian history, the hematite blueberries found by the Opportunity rover in What's Up. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. For decades, scientists have studied the red dust coating Mars and developed a strong working hypothesis about what gives the planet its distinctive color. The leading idea was that iron in the soil reacted with small amounts of water and oxygen over long periods to form hematite. It's a familiar form of iron oxide, or rust, that we have here on Earth. This fits well with our broader understanding of Mars as a cold, dry planet that once held water but lost it billions of years ago. Earlier studies of iron oxide and Martian dust, based primarily on spacecraft observations, did not detect any water bound within the mineral structure. This led researchers to conclude that the dust must be composed of an anhydrous hematite, anhydrous meaning it doesn't contain any water. The hypothesis was that hematite formed under dry surface conditions through reactions with the atmosphere long after Mars's early wet period ended. But science is constantly evolving, and new data adds an important layer to the story. Recent findings led by planetary scientist Adam Valantinas, who's a postdoctoral fellow at Brown University and formerly at the University of Bern in Switzerland, suggests that the red dust might actually be dominated by a different kind of iron oxide, ferrihydrite. That's a mineral that holds water in its structure. Adam's team combined orbital and rover data with carefully controlled lab experiments. By simulating Martian dust and analyzing how different iron-bearing minerals behave in Mars-like conditions, he and his colleagues discovered that ferrihydrite provides a much better match to what we actually see on the planet's surface today. This discovery doesn't overturn what we know. It deepens our understanding. It suggests that Mars may have rusted much earlier than we previously thought, while liquid water was still present, and that the red dust we see today is a relic of a wetter, more complex climate history. Adam's team's new paper called Detection of Ferrihydrite in Martian Dust Records Ancient Cold and Wet Conditions on Mars was published on February 25th, 2025 in Nature Communications. Hi, Adam. It's wonderful to have you on to talk about this.
Hi, Sarah. I'm very happy to be here.
Almost everybody knows that Mars is red. Even children know that it's the red planet, but trying to figure out why Mars is red turns out to be way more complicated than we thought. When did you first think to question this long-standing idea that Mars is red because of hematite?
Yeah, so I was, thinking about this question during my PhD thesis time. I started my PhD in the University of Bern in Switzerland back in 2018. And perhaps during, midway towards the completion of my PhD thesis, I was reading these papers and also textbooks actually on the exploration of Mars and what we know about the surface, the surface composition, physical properties and mineralogical properties. And, I was kind of inspired by the wealth of knowledge that has been generated, for the last decades since the age and the birth of spacecraft observations and the exploration of Mars since like 1960s. And the question of why Mars is red has been, tackled by several authors and several scientists. And, when I was reading the literature and, comparing what we know now and what we knew before, I kind of noticed that there are still, unanswered questions about the composition of Mars, and especially the composition of the Martian dusts. The dust is the carrier of the color of this rust mineral. And then I decided to, reinvestigate and revisit this problem that's been discussed since the 60s. And then as I revisited, I started seeing something interesting. So we can talk about this as well later. Yeah.
Well, your paper suggests that ferrihydrite is the reason why Mars is red and not hematite as we originally thought. Can you explain the differences between these two compounds?
Yes. So both of them are iron oxides. So, as you look at, for example, metallic surfaces on Earth, they rust. So it's a similar process that's happening on Mars. You need the material that has iron. And this iron is a certain kind of specific chemical composition that changes its properties when exposed to oxygen and water. And then this iron forms this iron compound known as iron oxide. And these two minerals, so ferrihydrite and hematite, they are different because hematite does not contain water in this chemical structure, and ferrihydrite contains water in its chemical structure. So that's why it's called ferrihydrite, meaning it's hydrated, water containing. And by looking at, and by understanding which type of iron oxide flavor there is on Mars, we can tell about the environmental conditions and the question of if there was liquid water, for example.
What conditions are necessary for ferrihydrite to form versus this hematite?
Yeah, so hematite was thought to form, hematite can form actually in several different environments, but the environment that was kind of canonically favored, it was an environment that was water poor. So people thought there was no liquid water that could interact with these iron minerals. So for example, basalt is a type of volcanic rock that contains iron. And, they thought that you can form hematite just by oxidizing magma. So as magma erupts on the surface of Mars, maybe there's some traces amounts of oxygen, and that forms this hematite. But ferrihydrite, on the other hand, is formed, especially on Earth, in environments that are water-rich. You need liquid water, and you need also oxygen. So on Earth, that you need atmospheric oxygen for ferrihydrite to form, and water. And it can be found in, iron-rich streams, aquifers. It can be found on the ocean floors. It can be found in lakes. It can be found, even in, sewage waters of iron mines. And so it's a widespread mineral. But the thing is, with ferrihydrite, it's a very young mineral. Hematite, on the other hand, it's found in old rocks. Ferrihydrite, in contrast, is a young mineral. So we thought that on Mars, the one reason that ferrihydrite could form is to have brief interactions between liquid water and rocks, or you need very low surface temperatures and very low water temperatures, so maybe near freezing. And you could sustain that perhaps when you imagine these huge amounts of ice. And maybe you could have, volcanic eruptions that would melt this ice, and then this ice would be maybe very cold. So this water would be very cold, and it would, form these flash floods, and these flash floods could maybe chemically weather and interact with the rocks and form ferrihydrite.
I mean, there are so many different repercussions of everything you just said if this is the case. What does this do to our understanding of the timeline of water on Mars?
Yeah, so this is also, kind of an interesting question because there was this mineralogical model that tried to, it's a great model. A lot of the observations that were made and concluded based on this model are correct. But, with science, that's how it is always, we have to think of science as ever evolving, and it's never static. It's always dynamic. You have to refine and improve your theories. So what I'm saying is that with this model, it's called the Bibbering model. It's a model that explains the mineralogical evolution through time on Mars. And You have the Noachian period, you have the Hesperian period, and Amazonian period, and for each period of these periods, the observers and scientists attributed a specific mineral formation. So the Amazonian period was thought to produce hematite. So 3 billion years of Martian geological evolution, the authors proposed hematite. So they thought that maybe hematite can form early on, as I said, through magmatic and oxidation of magma. But over time, you can maybe oxidize very thin layers of rocks on Mars through these traceless amounts of oxygen. And they thought that this process continued for 3 billion years. But what we see is that if it's not hematite and ferrihydrite, you need liquid water. And we know that liquid water on the surface of Mars currently is not stable, but there was much more liquid water in the past. There are also other multiple lines of evidence that also support this. So we're not the first to say that there was liquid water in the deep Martian past. But what we are saying is that the dust, and this rust mineral formed long ago, and it's not a contemporaneous recent geological process that formed this mineral. So basically, we're pushing the timeline back and saying that in the past, maybe 3 billion years ago, there was interaction between liquid water and volcanic rocks. It formed this rust mineral. And then over time, Mars lost its atmosphere. It became hyper-arid. And once you have a hyper-arid environment, you can create dust because through erosion, wind erosion, you can erode rocks and surface materials. And as you erode, you make this dust. And, on Earth, for example, we know that, the Sahara Desert or any type of desert environment that is very arid. And if there's no rainfall, dust accumulates. And as there's no liquid water, no precipitation, dust can accumulate. And on Mars, this dust then gets spread around by winds and global dust storms. So, and basically that's how this characteristic red hue arises on Mars, is through erosion of these ferrihydrite-rich rocks. That was kind of the concept model that we proposed in our study.
That is interesting because I was going to ask, if there was water on Mars in large amounts, it would be in certain locations, which means that you would end up with some places with way more of this ferrihydrite versus other locations. But if Martian dust storms are actually the thing knocking it around, that would explain why the entire planet ended up red instead of it just being congregated in areas, which is almost unfortunate because it would give us an even more deep understanding of where water was localized on Mars during those times.
Yeah, this is a very good point. Dust is obscuring the signal. It's spotted in a lot. There are source regions, and there are also regions where it accumulates, and that really makes it difficult for us to understand where these ferrihydrite-rich rocks are. But our team is confident that there are some tools and instruments that can help us address this question. So this is actually something we're thinking about for the next project.
Well, this study combined spacecraft data from Mars Express, the Trace Gas Orbiter, Mars Reconnaissance Orbiter, and of course, the rovers as well, Curiosity, Opportunity, Perseverance. How did you bring together so many different sources to make this discovery?
Yeah, so, in science, if you find something interesting, you always need to provide solid evidence. And the more evidence you can provide, the better, because especially if you're finding something that contradicts a former theory, you need to build confidence in your result, in your conclusions. So what I did is, I looked at I looked at multiple data sources, as you just mentioned. Also, not only I used spacecraft observations and data, I used also rover observations and laboratory experiments. And the exciting thing is that all of these instruments and all of these data, they supported the initial observation and the initial conclusion that ferrihydrite is the dominant iron oxide present in the Martian dust.
What would you say are some of the biggest challenges of actually trying to figure out the composition of this dust using instruments in space or even on the ground? Because we can't, obviously we don't have Mars sample return yet, so that's a little challenging.
So I would say that the biggest challenge is probably learning all these different instruments and understanding the data, because to understand the data you need to know how the instrument functions, what are the caveats, what may be the likely artifacts, and difficulties in working with the data. So I think none of these challenges cannot be overcome with with the work and just perseverance and motivation. So, step by step, as I started my PhD thesis, or this project during my PhD thesis, I continued working on this during my postdoc time. So at Brown University with Jack Mustard as my supervisor. And, you just need time, just need work, and things, go your way if you just persevere. So this project took me about 3 years to complete, actually. Yeah.
Oh, wow.
Yeah.
And clearly understanding how these instruments work was really pivotal to the way that you analyze the samples in the lab. Because you didn't just use, our normal methods of analyzing these things in the lab. You wanted to mimic the way that spacecraft and rovers would do this kind of measurement on Mars to actually compare the two. What was that process like?
So one of kind of the established methods in Mars observation or remote sensing observations of Mars is to acquire a spectra of the Martian surface. So a spectrum is basically, it tells you how much of light is reflected at different wavelengths. And by, these, the shape and absorption features and the amount of light basically that gets reflected, you can, from the surface of a planetary material, such, a planetary surface such as Mars, you can tell something about the composition of the surface. However, if you compare these observations done by spacecraft and rovers, as you mentioned, you're not there. We don't have the samples here on Earth, so we cannot compare directly. So we have to make our own simulants. So in the lab, we synthesized with the help of one of my colleagues these different iron oxides. And actually, I didn't mention this, but on Earth there are at least 10 or more iron oxides. So there are these different flavors of iron oxides. So I looked at all of them in the lab, and I was mixing them with the basalt. And these mixtures, then we analyzed them using reflectance spectrometers. So similar type of instruments that are on the rovers and on the spacecraft. And then that gives us direct comparison in understanding, what is the actual composition of the Martian dust. It helps us to really pin it down and understand what are the major mineralogical phases present in the Martian dust.
Martian dust is really fine. How did you go about getting these tiny, tiny, tiny little dust grains?
Yeah, so that's another thing that we did. Not only we looked at different minerals, but we also looked at physical properties. So we know that the Martian dust is extremely fine, just because it's sticky. It's you can see it in the rover images. All this reddish hue. It collects on solar panels. Several rovers on Mars have been really suffering because of this dust, because it just covers the solar panels, and then the instruments, there's no energy generation, and these rovers just they just stop functioning. So it's everywhere, and this small particle size is also has an effect on the spectral properties. So it has an effect on the way light is reflected from the surface. So basically, to mimic these particle sizes, we use this advanced machine in collaboration with our colleagues at University of Grenoble in France. We're grinding our powders, so we really approached particle sizes of close to or even smaller than a human hair, about 60 times smaller than a human hair.
Wow.
And so these particles are really, really fine. And we did see that actually after grinding, the results were fitting much better to the actual Martian observations.
Were there any things that were actually mismatched between this combination of ferrihydrite and basalt with what we actually see on Mars?
Science is that's the beauty of science. It's very difficult, or maybe even impossible, to always have a perfect match. So we did see, for example, that there are these effects in the near infrared range. So what we focused on in our study specifically was the visible range. But we also looked at the near-infrared range, so which is basically longer wavelengths of light. We saw that there are these effects that may result from the way how particles and powders agglomerate and cement to each other, and you may see subtle differences in the shape and the slope of the continuum. So this is basically a fancy term for features as part of the spectrum, and if it's inclined or slightly, or if there's a downturn. So we saw that, between our data and the observations, there's a slight difference, but this is quite minor.
Well, it's one thing for ferrihydrite to form on Mars, but as you said, it's a totally other thing for it to remain stable for that long period of time. So how did you test to see whether or not this would break down in Martian conditions?
Yeah, so this was another set of experiments that we conducted, and this was in collaboration with our colleagues at the University of Winnipeg in Canada. So as you see, as you have noticed, this is was quite a laboratory-led project. As I said, I started working in University of Bern, then University of Grenoble, Brown University, and then University of Winnipeg. So basically what we did is we sent a few samples to our colleagues at University of Winnipeg, and they have a Mars chamber. So basically a Mars chamber is it's basically a kind of a closed system, a closed container where you put the samples in. You can regulate the environmental conditions such as temperature, relative humidity. You can also shine the samples with ultraviolet light and simulate the radiation environment that's present on Mars. And then you can test how all of these parameters, how they affect and how they change different properties of your samples. So what we're interested in our case, was to look at the mineralogical structure of ferrihydrites, how the atomic structure, basically how the atoms of ferrihydrites, and if the atoms and the atomic structure in ferrihydrite is affected by the Martian conditions, simulated Martian conditions, because there was this idea that ferrihydrite is not stable on the Martian surface, and that it would change, that it would not be present, and it would crystallize and change into, for example, hematite. That was like one of the prevailing ideas. So we decided to test this hypothesis, and what we saw was that there was no change. As you put this ferrihydrite in this chamber, you crank down the humidity, you fill it with carbon dioxide, you shine, ultraviolet radiation at it. Nothing happened. We saw that the crystal structure of ferrihydrite remains the same because we also did another measurement just after dehydration. So this experiment is dehydrating the sample. And then we did X-ray diffraction measurements. So we took an X-ray diffraction pattern of ferrihydrite before the experiment, and then we took a second pattern after the experiment. And then again, comparing these two data sets, we saw no difference. So ferrihydrite is poorly crystalline, it's very disordered mineral, and there's no change in ferrihydrite structure.
But we are talking about timescales that are like billions of years long. Can we extend that out that far?
Very, very good question. This is actually one of the questions that not only a few of my co-authors asked, but also the reviewers asked during the review process. So what I did is I looked at the literature and at the theory. So there's this a law or equation called Arrhenius equation, and it's quite widely used in the chemistry and the geochemistry communities. And basically it tells you that certain kinetic reactions are very dependent on temperature, actually very dependent, so super sensitive. And so we have to think, about the temperature regimes on Mars. Mars is very cold right now. The average surface temperature is minus 70 C, so Celsius. So very cold, well below freezing temperatures. And these actually surface temperatures, they slow down a lot of kinetic reactions, a lot of these reactions that would be happening on Earth, but they don't happen or are extremely slowed down on Mars. And basically, I employed these theoretical calculations, which also suggested that ferrihydrite is basically in some sort of, it's in a frozen state. It will not crystallize and change into other iron oxides just because it's very dry and also very cold. And this was great because these theoretical calculations, they agreed with our laboratory experiments.
And if we combine this with the understanding of the conditions under which these two different iron compounds form, this could potentially tell us a lot about whether or not Mars had this warm kind of, wet past, or if it was mostly cold and icy.
Yes, so we discussed this in the paper as well, because we know from, as I mentioned before, from several past studies that investigated the mineralogy of the Martian surface, both from orbit and from ground. They have identified various hydrated minerals such as clays and sulfates, and this has been known since maybe 2005. So now 20 years we have known that there are all these other hydrated minerals. So we discussed that perhaps these clays and sulfates, they perhaps formed before ferrihydrite. So you could have had maybe warmer conditions early on, but then the surface environment started to become more cold and dry. And perhaps the formation of ferrihydrite suggests that it formed during the latest gulps of watery Mars history. Maybe it was the last stage of these mineral formations as water was becoming colder, more brief, maybe more episodic, and then at some point completely dry.
Both of these iron compounds also require some kind of oxidizing environment in order to form. And we don't have a lot of oxygen in the Martian atmosphere today, but there is some indication that there was more oxygen in the past. I think there have been some studies on like manganese oxides and other things found on Mars that suggest that it did have a lot more oxygen in the past. But what other sources of oxygen could potentially lead to the creation of these chemicals other than that?
Yeah, great point. This is also something that we have discussed quite a lot in the team, but also with several scientists in the community. So on Earth, as you mentioned, these iron oxides, they form because of atmospheric, they require atmospheric oxygen, and the Earth's atmosphere is very oxygen rich, which is not the case for present day Mars. However, in the past, there may have been a bit more oxygen, but we had to agree that perhaps free atmospheric oxygen was not required for ferrihydrite formation. And, there are alternative chemical pathways that would result in ferrihydrite formation. So, for example, you can create oxidants in the waters just by shining a UV light. The process is called photooxidation. So as you shine UV at the water, it creates these OH radicals. So these compounds that can react with iron and oxidize the iron so you just need the liquid water. You can also form some traces of free oxygen by photolysis. So if you're shining a UV light at water molecules in the vapor form, it splits them up into hydrogen and oxygen, and perhaps some of this free oxygen then created by photolysis can react with iron and oxidize it. So what I'm trying to say is that there are multiple pathways how you can oxidize iron minerals and manganese, for example, manganese-rich materials, and perhaps large amounts of oxygen is not required. So, but this is something that we are thinking about for future work, and maybe we find a way how to distinguish between these varying hypotheses.
We luckily have some really wonderful missions coming up that could help us try to sort some of this out. I'm really looking forward to the European Space Agency's Rosalind Franklin rover, but also we're really pulling for that Mars sample return mission over here, because getting those samples could potentially shed light on a lot of these puzzles that are going to be really difficult to solve otherwise.
Yes, definitely for Mars exploration, these are exciting times, and the Franklin rover includes a drill, so they can actually, drill into the subsurface for up to, I think, 2 meters depth. So you could potentially look at if there's a difference in oxidation of the surface materials as you go and drill deeper into the Martian subsurface, and that could also actually tell us about, what kind of oxidizing environment was present on ancient Mars, but also modern Mars, because Mars is, although it has a very thin atmosphere, there's still processes happening on the surface that are interesting and we can investigate.
We'll be right back with the rest of my interview with Adam Valantinas after this short break.
Hi, y'all. LeVar Burton here. Through my roles on Star Trek and Reading Rainbow, I have seen generations of curious minds inspired by the strange new worlds explored in books and on television. I know how important it is to encourage that curiosity in a young explorer's life. That's why I'm excited to share with you a new program from my friends at the Planetary Society. It's called the Planetary Academy, and anyone can join. Designed for ages 5 through 9 by Bill Nye and the curriculum experts at the Planetary Society, the Planetary Academy is a special membership subscription for kids and families who love space. Members get quarterly mailed packages that take them on learning adventures through the many worlds of our solar system and beyond. Each package includes images and factoids, hands-on activities, experiments and games, and special surprises. A lifelong passion for space, science, and discovery starts when we're young. Give the gift of the cosmos to the explorer in your life.
It's funny that after all this time, all of this research on Mars is so much that we still don't understand. Do you think that this finding suggests that there's potentially other minerals and processes on Mars that we might have completely misunderstood?
Well, we know a lot about Mars, and I think it's quite possible that there are things that perhaps we have not thought about, and they're just there in the data, which is just we need someone who looks and revisits all these great data sets that we have for Mars. And I think it's quite likely that we could find something that's not been thought about and not discovered. Yeah.
Well, it feels weird to characterize it as completely misunderstanding. I mean, even in this case, we're literally just debating over whether or not it's this flavor of iron compound versus this flavor of iron compound. Like, we understand a good amount of the way that this is falling out. It's just about which one and what timing and what initial conditions, which is going to take us a bit to figure out. But I mean, it's quite remarkable that we're at this point.
Yeah, and one of the reasons why sometimes we find something new is because our instruments and our data sets are improving. So the early Mars exploration was done using ground-based telescopes, for example, and we did not have spacecraft or rovers there, and these scientific conclusions and observations were quite limited in the beginning. So as our instruments are improving and as our data sets are improving, we can actually refine a lot of these questions and advance our knowledge of Mars' geological history and evolution and the environments that were present not only on present-day Mars, but also ancient.
If this is the case, then Mars would have rusted when it still had water present on its surface, and that means the red color is more of a sign of a wetter past than this slow oxidation process. What do you think this suggests about the history of habitability on Mars?
So life as we know it requires liquid water. NASA even has a mantra called follow the water. So for a Martian exploration, tracing the water and understanding where the water was is quite important, especially for habitability question. So by identifying that the Martian dust or this iron mineral contains water, that tells us that liquid water was required, and by this inference, you can maybe argue that that raises the habitability potential of Mars, because now everywhere you look, basically, because dust is everywhere, you have some water that's trapped in this mineral structure. So perhaps we are at this point where evidence for liquid water in the ancient past can be observed right now almost everywhere. You have ices in the poles, which are not only carbon dioxide, but they are composed of water. You have these clay minerals and sulfates that I talked about, which have been discovered in the past. The dust is a carrier also of hydration and evidence for liquid water. So I think all of these lines of evidence they suggest that the conditions for life may have been present on Mars, and now we just need to basically find the evidence, which is, I guess, the most difficult part of Martian exploration. However, we have Perseverance rover and also Curiosity rover who that are investigating these environments that contain liquid water, and perhaps they can address these questions. I've been looking at Mars images for most of my career, but sometimes I still get excited just by looking at all these amazing images that have been acquired by Perseverance rover, but also by spacecraft data. But to note, actually, you mentioned something interesting about human exploration of Mars. So this kind of an observation that we can make from just the evidence of ferrihydrite in the dust is that human explorers, once they land on Mars, suppose they land somewhere where it's very dry and there's no ice in the subsurface, they could potentially, use Martian dust and ferrihydrite to cultivate this water because, ferrihydrite is hydrated. So there is probably something maybe up to on an order of 10% by weight of water in this mineral structure. So you just need to heat it up really strongly and condense the vapor, the gas released from ferrihydrite, and you could use this perhaps as a resource.
Mark Watney would have wanted to know that during his not real time on Mars. No, but that's a great point. This does have some implications there. Then, and we're going to need that if we're going to do it. Although we're also going to have to figure out that whole perchlorate issue. There's a lot there going on, but each and every clue that we get takes us a step closer to being able to put humans on another world in our solar system, and it's just amazing. But you touched on this a little bit earlier, that you do have some future plans for your research. Do you want to talk a little bit more about what you're going to be doing next?
The discovery of ferrihydrite on Mars opens several research directions, and it raises several interesting questions. So one of the questions is constraining the timing, so trying to understand when the oxidation happened, because right now we just use the abundance of liquid water on ancient Mars as perhaps the time when ferrihydrite formed, and we mentioned something about 3 billion years ago, but we need to constrain this and understand how long this could have happened, and then for that you need to look at the geology, and this is one of the kind of the research directions that we will take in the future. Another thing is to understand how ferrihydrite forms. So I mentioned to you that on Earth there are various environments, but perhaps on Mars there are geochemical pathways that we have not thought about. So I intend to look at ferrihydrite formation in the lab. So basically synthesize this mineral in various different ways, exposing it, to Mars-like conditions, changing the temperature, changing, the atmospheric composition, and seeing how that affects ferrihydrite formation. And, from these laboratory experiments, we can maybe understand something very fundamental and very interesting about the surface processes on ancient Mars.
So cool. Good luck with all your future research. And I'd love to know more if you actually do these experiments and find out something cool, because I'm just kind of mind blown that we're still in the situation where we're still finding out cool new stuff from old data and combining it with lab results the way that you did. Really clever. That's awesome.
Yeah, thank you so much. Yeah, it's exciting, and especially I did not mention, but the Mars sample return mission hopefully will bring back samples, and in those samples you will have dust, because as I mentioned, dust is everywhere. It's sticking to every single object on the surface of Mars. So you'll have some contamination of dust, and if we study these dust particles, we can test this hypothesis and really understand, if this ferrihydrite is present on the Martian surface, although I believe it is, but, we always need to test our hypotheses. But not only is it important for testing the hypothesis, but also just by studying the chemical composition of this ferrihydrite in the return samples can tell us a lot, because you can look at stable isotope measurements. So it's a type of analysis that looks at isotopic composition of ferrihydrite, and that can tell us about water temperature during the formation of ferrihydrite. It can also tell us about the source of the water. So, for example, it could tell us if it's meteoric or marine. So, if it's from precipitation, or, for example, if it formed in oceans. And also it can tell us also something about habitability, because we know that on Earth, microbes interact with a plethora of minerals, and iron oxide, namely ferrihydrite, for example, is known to be an important agent for these microbial reactions. And, there are several different things we can test by having the Mars sample return happening and, looking at ferrihydrite present in these samples.
I cannot stress enough how much I want those samples to actually reach Earth. We're, as an organization, trying to advocate as hard as we can for Mars sample return. It's going to take some time and some work, but whether or not these samples come home sometime in the next 10 years or some other time, eventually humanity is going to get their hands on something from Mars, and we're going to be able to figure out these questions. And I'm so excited. I want it to happen yesterday instead of 40 years in the future.
Oh, yes, definitely. I mean, the scientific community is also extremely excited about the prospects of having the samples back. And, I hope that maybe one day, if the samples are brought back, maybe, one of my future students can look into it and, test these ideas.
I love that. And then they can use your research and all the other people that have come before, combine it all together, and the things we could learn. It's going to be a beautiful future when we get all this back.
Definitely. I mean, my research is, based on, all the previous research from the community. So we're standing on the shoulders of giants. And I mean, that's the beauty of science. You're building, and, the future generations can also provide something very interesting.
Nice Isaac Newton reference. Well,
yes.
Thanks for joining us, Adam. I really appreciate it. And good luck in your future research.
Yeah, thank you so much for having me. I enjoyed this interview.
If you'd like to get deeper into this research, I've included a link to Adam's full paper in Nature Communications, along with a great write-up from the European Space Agency on this week's episode page at planetary.org/radio. Of course, Mars has been surprising us for decades. One of the most memorable early clues to its watery past came from the Opportunity rover, which discovered tiny hematite-rich spherules scattered across the surface, nicknamed blueberries. They told a very different part of the story, one shaped by groundwater and chemistry. Here's our chief scientist, Dr. Bruce Betts, for What's Up. Hey, Bruce.
Hey there, Sarah.
I'm back from my big whirlwind city adventure in DC, and also our beautiful gala. It was nice to see you there.
It was nice to see you there. That was actually my double.
Your clone?
I hired to go to events. Yeah.
Yeah, man. It wouldn't be bad to have a clone just so she could do some extra editing, maybe go off to Mars, pop back, and tell me how it was.
Sarah, too.
I think this research paper is really interesting in that, we had a general concept of what was going on with Martian dust, but even with all of our data, there's still some wiggle room in the chemistry there. So I think getting those samples back will be honestly very helpful. But even so, it's not like we didn't understand what was going on with Mars. We're just kind of refining our understanding of which particular iron oxide. So it's cool that we're in that place.
Hardcore mineralogy.
Hardcore. I wanted to bring this up with you because I think even for me, one of the big things that pointed to the fact that Mars had liquid water in the past was this discovery that blew up in newspapers and on social media about these so-called blueberries on Mars that Opportunity found. They're not actual blueberries. I've even heard little kids ask me why there's blueberries on Mars, thinking that they're legit blueberries. So I wanted to bring this up and talk a little bit about how that relates to hematite and this broader discovery of what kind of iron is on Mars. So could you tell us a little bit about what went down with opportunity and why was that discovery so awesome?
Okay, first of all, what? They're not actual blueberries? Okay. No, I know this. So I'm going to back up a little bit and take the picture out to Spirit as well, the Spirit rover. So Spirit and Opportunity were sent at the same time, and landing sites, obviously 2 landing sites were picked. And it was interesting because Spirit's landing site was based mostly on geomorphology. So it was put into a location at the end of a big, hundreds of kilometer long valley channel that presumably liquid water had flowed in, and that's how they picked where they went. This is shortening a story that took months and years of scientists arguing about it. But the Opportunity site was chosen based on spectroscopy and perceived mineralogy. So using the thermal emission spectrometer on Mars Global Surveyor and complementary data, they saw one of the few places on Mars that showed a spectra that should have corresponded to coarse-grained hematite. Coarse-grained hematite being a gray mineral that you may have seen often made magnetic and used in jewelry and things like that. Well, it turns out that is very exciting for those playing the liquid water game, which people play because liquid water is needed by all life on Earth. And so finding a place that seemed to have coarse-grained hematite was a party when you're looking for water, which might have something to do with life. So when it landed, this was the era of airbag landings. So you inflate airbags around the entire spacecraft, and when it lands, it bounces, and it bounces and it bounces and bounces. It's very Tigger-like in that respect. It's and they referred to Opportunity as being a hole-in-one because when it bounced after bouncing a kilometer or 2, literally, it ended up in a very small impact crater. And so one of the first things it saw was the miniature cliffside of the impact crater that showed exposed sedimentary layers, and it showed blueberries, which I'll get back to, but coarse-grained hematite all over the place. And this was very exciting.
But really, though, the fact that they managed to get a kind of hole-in-one after practically bubble wrapping a rover and dropping it on Mars is kind of spectacular.
It was. And if you look at those initial images, it was very confusing, at least for those of us not truly in the details of the imagery, because it looks like you've got like a 10-meter cliff that you're looking at, and it turns out it's like 10 centimeters. And but still showed multiple sedimentary layers, and there are these things all over, these little spherules, so little spheres that when you look at them, particularly in a false color, they look bluish. And in fact, they are bluer. They aren't really blue, but they're bluer than all the red stuff all around. And it turns out this stuff's all over where they landed when they went out and they drove on the planes. Why is this important? Because it's associated, again, with usually, almost always on Earth, with liquid water creation and things like hydrothermal systems and the like. So to get that instant confirmation, or practically instant, was just a wonderful contrast. So you take Spirit, it was the very end of years into the mission where it got its most powerful examples of things that look like they formed in liquid water in terms of seeing them on the surface. Again, you've got this huge channel flowing in. Anyway, it was groovy, and as soon as they were called blueberries, the name was stuck.
But this leads me to another question, which is that if coarse-grained hematite is this bluish color, then why would people attribute the red dust on Mars to this bluish iron oxide?
Well, it's more grayish in reality in
That's fair.
Earth, but still, it's a valid question. I will admit that I'm not entirely sure, but I think it is because there is also fine-grained hematite and permutations therein, and that tends to be reddish on Earth and is also can form in aqueous water environments or not as much. It would be a different form of how you arrange how you pile up the molecules in a crystalline lattice.
Every time I learn more about Spirit and Opportunity, I mean, I've heard this story so many times, but it still completely blows my mind that that rover basically mission accomplished itself on day one and then went on to have 14 years almost on Mars, so far beyond what we ever thought it was going to be able to do. I don't know. I'm really looking forward to the day that we have these kinds of rovers on every single terrestrial world, because just imagine what we could learn with one of these going around on Mercury or even the moons out there. Ugh, it would be so cool. Why don't we go into our random space fact for the week?
So I'm going to talk about ancient astronomers and their accomplishments. So the Mayans have got a lot of bad rap for their calendar and have other reasons for bad raps. But in terms of their science and astronomy, they were amazingly spot on for how little they had in terms of equipment, essentially none. They were able to predict eclipses of solar and lunar eclipses accurately. They have their setups of, for example, in Chichen Itza in the Yucatan Peninsula, you have things where on the equinox, a shadow appears. I don't know if you've ever seen the picture of the Castle El Castillo, the pyramid, and the shadow appears looking like a feathered serpent it was designed for, but it's on the equinox that it highlights that symbol. And they also had an observatory aligned to study Venus's movements. Now, an observatory didn't have a telescope in it that we are aware of, but was a isolated place that is for astronomical observation. There you go. Mayan astronomers, well played, sirs. Well played. Good stuff.
I mean, that's dedication right there. Learning enough about space that you can track that kind of stuff so you can build your buildings in such a way that on one particular day, something happens. I was wowed by that when I was a kid in my hometown. We had a building. It was an old California mission where the sun at its peak, when it hit that meridian in the sky, would shine right through a hole in the wall on the winter solstice. I mean, just for that one moment, that is a really beautiful dedication and just a statement about how deeply these things are embedded in different people's cultures.
And there are, civilizations, various places that had this type of thing. And of course, one of the fundamental things was understanding the calendar to understand, assuming you're at the age of agriculture, to understand when you should be planting crops and what the sun's doing and things like that.
Right. So, and now people can't even see the night sky because we have too many lights.
Yeah, but we have professionals who are now far more adept at those things.
That's fair.
Because, satellites. So lights in the sky, can't see as well. Satellites. No, very little atmosphere, depending where you are.
Right.
Now, what is this? I'm trying to be the positive one? Come on. Don't put me in that position.
Too late now, Bruce. Now you're the positive one. Deal with it.
Oh, I would like to. I think that's a very great opportunity for me going forward. All right, everybody, go out there, look up the night sky, and think about the most positive thing that you have thought of when looking up at the night sky. Thank you, and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with our Cosmic Shores Gala, the Planetary Society's 45th anniversary celebration. Anytime you get that many space fans together on a giant boat, you know you're going to have a good time. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review and a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email at planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members who stare up at that red planet from this pale blue dot we call home. You can join us as we work toward a brighter future for Martian exploration at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. And until next week, Ad Astra.